Hello appraisers, this is Brandon with Spark for Appraisers, and in this video we're going to be covering a few extra details about regression, not necessarily a different type of regression like we've covered in the last videos, but just some items related to regression. And you'll see on the screen here I put R squared or lowercase r squared. There, R squared is referred to as either a capital R or a lowercase r, depending on the situation. And then also data points. How many do we need? So let's go ahead and get into it. And by the way, right off the bat, I'll apologize. I said in the prior video that we'd be getting into paired sales in this one, but I realized there was a few extra things we needed to cover first regarding regression, and then in the next one, we'll hopefully move on to paired sales analysis. Okay, so let's get into it. R squared, what is it? Well, first of all, in a very basic way, R squared is just taking the R and then squaring it. Now, obviously, that's very basic and obvious, but now to get down to it, let's talk about what R is. So R is the correlation coefficient. So I'll just write that in here. And essentially, what that is R can be any number from negative 1.0 to positive 1.0. And a positive 1.0 is a perfect positive relationship between the two variables. And so let's just go ahead and show you what that would look like. So it basically means that where one variable goes up, for every point of that variable or every unit of that variable, then the other variable goes up as well. And so just to give you a little example here, we'll draw this, and let's go ahead and draw some points here. So as the x here goes up, then so does, whoops, the y. So we'll do that, and then that. So every time I go to the right on my x, I'm also going up on my y. And so every time the x is going up, the y is also going up. Now, for the opposite here, let's get rid of those. That, what we were just talking about was when there was a positive 1.0, but now let's talk about the other case, which is a negative 1.0. And this is a perfect negative correlation. And what we mean by that is that for every unit of one variable that goes up, the other goes down. And so that would look more like this. Every time we go up in x, we're going down in y. And so that would be a perfect negative relationship, and that would be a negative 1.0. Now, to talk about reality for a minute here, this almost never happens in real life, and what we have more often is, sometimes you go up or down, but your overall trend might be down, but it's not perfect because sometimes it goes up as you go to the right and sometimes it goes down. For example, you might have a house that sells for 1,000 square feet that sold for, let's say, 150,000. And then you might have a house with 1,200 square feet and it sells for 160,000. But then you have a house that's 1,350 square feet and it sells for 155. So in this case, we went up in GLA, but the price went down, and that could be for various reasons you can think of. But this would be a non-perfect positive relationship, and that's kind of illustrated by this, although this would be a non-perfect negative relationship in this chart. So that's all we're talking about, and that's what R represents, our correlation coefficient. It's any number between negative 1.0 to positive 1.0. And so just to give you an idea, a zero, if it was zero, it might look something like this. Let me just draw a bunch of dots in here. And so this is like nothing. It's basically just going straight across pretty much, and there's no real relationship that we can define. And so in that case, as we go up in one, the other doesn't really do anything. It doesn't go up or down. And so that would be an example of R equals 0. Okay, so now let's translate that into R squared. All right, well, let's go ahead and keep in here the -1 to +1. Let's make that 0.0. So -1.0 to +1.0 is what r can be. And again, that's our correlation coefficient. And r squared is basically just whatever this number is, some number between -1 and +1 squared. So if we had, for example, an r of 0.8, then that would mean that our r squared would be 0.64. It'd just be 0.8 squared, so 0.64. And then there are other ways to calculate that, though, and we won't get into all of those, but suffice it to say that when we square a number between -1 and +1, then our answer is going to be somewhere between 0, let's say 0.0, to +1.0. So obviously, if we square 1, we're going to get 1. If we square any number between 0 and -0.99 or +0.99, we're going to get something between 0 and +1. So that's what r squared is going to be. And often, if I'm sure many of you have already used Excel to perform some kind of regression, or maybe used other tools, and you'll see your r squared number. And often you'll be told that if you don't have an r squared over a certain number, like let's say if your r squared number isn't greater than or equal to maybe 0.7, then the results probably aren't very good, and you should just kind of throw that away. It's not meaningful. Now, what I would like to argue is that that's not true. There are, I believe, many cases where you can have a much lower r squared than 0.7 and your result are still valid. And so let's just get into a couple examples. And actually, first of all, before we even talk about that, what is r squared? What is it telling us? So let's just do a quick little chart down here. And r squared is basically telling us how well our predicted line from regression. And so let's draw a line. Actually, here, let's do this a little different. So let's say this data would have a line going up through it like this. And so obviously, our line that we got from running regression does not perfectly match the data. As you can see, there's many data points that are not directly on that line. We can see that it's a positive relationship, but it's not a perfect one, meaning every time I go and I plug in an x value, and let's say in this case, x is GLA, and maybe this down here is 1,000 square feet, and this up here is 2,000 square feet, then let's put a little SF, then this right here might be, let's say, 1,300 square feet. And so in theory, you could take the line for this, or I'm sorry, the formula for this line, which might be something like 70x plus, let's just say 80,000. And so we could plug in x into this formula, which in this case, x is going to be a GLA of 1,300. We can plug that in, multiply it by 70, add 80,000, and that tells us what our sale price is going to be. In this case, we're talking about x is GLA and y is sale price. So that would tell us. But we know in reality that you're never going to have a chart that looks like this, where you have perfect sales and they perfectly line up with the line from regression. So every time you go and pick a point, that matches exactly what a property is actually going to sell for. That's not going to happen in real life ever when it comes to real estate. So we know that we're not ever going to have an R squared of 1.0 when we're using real estate data. That's not going to happen. But this is what it would look like if we did have an R squared of 1.0. It's basically a measure of how well this prediction line matches the actual true data. So a 1.0 is a perfect match. All the dots would fall along that line. And the further away all your dots get from the line, the lower the R squared is going to go. Again, the more we add in here, away from that line, the lower the R squared is, meaning this line that we drew that from regression does not really predict the data well at all. Okay, so now let's get into, does this really matter for us as appraisers using this information for adjustment support? And I definitely wouldn't say it doesn't matter. It can be worth looking at. However, I would say just be really careful, because you can have very low R-squared numbers but have good results that are meaningful. So let's just show you an example of that. This is something I made last year as an example for some appraisers. Let's just zoom in on that. This is a plot, and this basically we ran ordinary least squares regression on these 50 points of data. So there's 50 points of data, and there are basically 10 days worth of data and 5 sales on each of those 10 days. We ran ordinary least squares regression on it, and we get this result: y equals 5,000x minus this number, which is where it would be when it crosses the y-axis, and with an r-squared of 0.205. Now, most people would consider this r-squared to be very low. And if you've taken statistics classes, you may have been told that when you get an r-squared this low, the results basically from that regression analysis are not meaningful. We shouldn't rely on them. And this is an example where that is untrue. So in this case, what's happened is, and right, I did this so these were each a day apart, but maybe imagine these are all a year apart, if that makes it easier to understand. But basically, we have 5 sales on this day, or you could say on this year, and then 5 more the next day, 5 more, and every single day, there's 5 more sales, and they're each $5,000 higher than the day before. So this sale essentially went up 5,000, then 5,000, then 5,000. So what is going on is every single day prices are increasing by $5,000. Yet we have a low R-squared here. So does that mean that this data is just something we should throw away and not care about? Absolutely not. In what we care about as appraisers is not, does this line perfectly predict what the sale prices are? Of course not, and that's not going to happen. We're never going to have a line with real estate data in here for sales and every single sale land right on this prediction line. That's just not going to happen. What we want to find out as appraisers is, what is the adjustment? Is this trend of this line, the slope of this line, is it giving me a good idea of how much values are actually increasing? In this case, yes, actually, it's giving me the perfect answer for how much values are increasing. Now, obviously, again, in real life, real estate data is not going to look like this, but this is just to illustrate the point that you can have a very accurate trend here. This linear regression is showing me exactly that things are going up at $5,000 a day. This is good data to use despite the low R-squared. And again, one more time, the low R-squared is because the actual sale prices are not right on the line. They're further away from it. Like right here, it's predicting my sale price should be 100,000 on January 1st. However, I've got sales at, well, 100, but also at 120, 140, 80, and $60,000. So some of these are very far away from that line, but that doesn't mean that this line or this slope of this line is doing a poor job of telling us what the market is doing. So all that to say, be very careful when looking at R-squared. The better thing to do, rather than just relying on R-squared, is to actually just look at the data, and you'll be able to see for yourself. I can tell by looking at this that, yeah, things are steadily increasing every single day at about, or at exactly, in this case, $5,000 a day. But what you might get is something that looks like this, where maybe you have, let's go, these are sales, and let's just say that in this case, X is GLA and Y is sale price. And so we might have some sales like this, maybe one way up here, down here, and then over here like this. And so you can see the data kind of it looks like it's kind of goes up, and then it goes down quite a bit, and then it goes up a little bit more. And so in this case, what the regression line might look like is something like this. But you know from looking at the data that that might not actually be true at all. It might actually be something where as GLA goes up, prices go up, and then maybe prices at some point go down again. That doesn't seem very likely, but maybe they go down again. But you can tell by looking at the actual sale prices whether or not this line is a good fit or for the actual data. Now, in this case, I would say no, but if we drew a very similar chart, and let's say, even though our data is really well spread out here, we can still tell in general that as I go up this way, I'm also going up this way. And so if I get a line that cuts through it like that, yes, that actually appears to be a pretty good fit as far as our concern as appraisers and trying to get an adjustment for GLA or lot size or whatever it happens to be. So even though I can't use this as a great predictor because I can see that, let's just say this number right here is 2,000 square feet. Oops, 2,000 square feet. Um, if that number, I can see maybe there's 3 other sales right at 2,000 square feet, and none of them fell on that line. So it's not a good predictor in that sense. This line won't tell me exactly what a house is going to sell for based on its square footage, but it could be a very good predictor of what the actual adjustment would be for, in this case, GLA. So that's kind of how we should look at R squared. Again, you can tell by looking at the data. I'm just going to do another example here. Now in this case, the line might actually be going kind of horizontally through it, and it might tell you maybe the GLA adjustment is $25. It's going up a little bit, but not much. But you can tell by looking at the data that's really not valuable information. The sales are just all over the place, so this is not something I should rely on. So again, regardless of the number you get for R squared, I would just encourage you to just look at the data in a scatter plot and judge for yourself whether it appears to be a good fit. And what that also kind of leads us into is our next topic, our last topic for this video, which is the number of data points and how many you need. So I've seen this debate many times for real estate appraisers as far as running regression or getting any kind of adjustment support, and how many data points do you need? And I know many appraisers were taught that they need 30 points of data in order to be able to rely on the results. And I would just say that if you go and just do a Google search right now, like how many data points do I need for any kind of regression, you'll typically find that you need a minimum of 10 per variable that you're measuring. So in this case, all these different types of regression we've been talking about in prior videos are all bivariate or simple regression, meaning we basically just have one independent variable and one dependent variable. We're basically just measuring one thing. We're trying to calculate one thing from one other thing. So in that case, based on that rule, we would need a minimum of 10. But what I'll show you here is that even that rule of 10 isn't really real. It just depends on the actual data. And so what I mean by that is, yes, 10 is a good rule for an absolute minimum, but it depends. Your minimum might be higher. I do think I would probably stick with the advice of those statisticians and go with an absolute minimum of 10, but the minimum might be higher in the sense that the further away your data is from that regression line, the more data points you will need to get a reliable number. And let me just go ahead and let's illustrate that. So, okay, this is our 10 points of data. And so the regression line might look something like this, where maybe it would go through there. And it's a slightly increasing trend line, but this is going to give us a high, I'm sorry, that is not true, a low R squared, because the data points, other than a couple, are fairly far away from that line. So we would probably get a low R squared number. And so what I'm saying is a low R squared means that you don't want to use 10 as your rule. You need more because this data might actually be doing something different than what it appears from these 10 points. So let's try this. And now let's draw the rest of those data points. Now let's say we have these data points. And now it actually appears that we have a declining trend. We didn't remove any of our prior data, we just added on data. And so our trend line, which was something like this, is now something like this. And this now appears to be a much more accurate representation of what the market is actually doing as far as declining. So as GLA goes up, our sale price is going down. That's what the market's telling us. Obviously, this is just a made-up scenario. But now that we have more data points, even though we have this, what's most likely a low R squared, we can reliably indicate that, yeah, as I go up in GLA, my prices are going down. It's not a perfect relationship. Sometimes when GLA goes down, you still have a higher price, like this one or this one. But in general, that is what's happening. And so in our market, for maybe a typical sale, then yes, we can say that it is declining. And again, the higher the R squared, the lower or the fewer data points you need. I would still stick with that minimum of 10 for a really high R squared. But in reality, you're probably not going to get very many high R squareds. You're probably going to get lower R squareds. But really what it boils down to is you want to be able to see, when you look at that data, can you see the actual trend? And so I can sort of see that, yeah, there's the high and there's the low, and that's pretty much what it's doing. Now there's a couple data points outside that line, but in general, that's what's happening. It's going down as my GLA goes up in this case. And that's what you want to look at, because if you can't see it yourself, then it's probably not something to rely on. And just like when we were talking about those people that say you need a minimum of 30. 30, maybe that's the case, but I do not believe it's always the case. Sometimes you might need more than 30. So let's take a look at this example where the data might look like this. And maybe you have a whole bunch of data points right in the middle, far away from the trend line. And then you have this. If I looked at that, even though I have, I'm guessing, at least 30 data points there, I am not going to use the result from this regression because this data is just all over the place. That does not really tell me anything. I have no idea what it is based on this. I would want to go use another set of data or another method to come up with my adjustment rather than relying on this regression line because that data does not appear to be telling me anything. All right, hopefully this was helpful in some way. I would say at the absolute minimum, 10. There, I can imagine a scenario where 10 would be enough if we had a chart like this and all 10 data points were like this. Then yes, I can imagine that's enough data. I would stick with the minimum of 10 that statisticians will say, 10 per variable. However, in many cases, because real estate data doesn't usually look this pretty, you are going to need more data points than that. Again, really low R squared, get a lot more data points. I don't have a set number to tell you, and I realize that's not super satisfying, but that's just the truth of the matter. What you need to do is go in and actually look at that visual, that chart, and see if you can see the trend and see if that regression line approximates that trend fairly well. Okay, that's it. Thanks everybody for watching, and we'll talk in the next one.